Okay. All right, I think it's time to start. Sorry about that. Loud. So some comments on the first exam. I graded some of it, as did all the other instructors for the recitations. And yeah, so I would encourage people to try to be a little more detail oriented with their computations. I noticed a lot of things being sort of left, like square root of 4 would be left as square root of 4 rather than just put it as 2. So sometimes there's some easy things to do to simplify the answer. We try not to take off points for these types of things, but sometimes they affect other things. But all in all, people did all right. There was a couple of hard problems on that exam, so I think that I was fine. If you want to look over the solutions, I did put them in files on Canvas, so you can go to Canvas and go to files, and I think it says exams and solutions is the folder it's in, and you can look over the solutions there. All right, so that is ancient history. Let's try to move a little forward. So I also, I should say, sorry, before moving forward, I put those histograms on the announcement. I don't know if people saw them or not, but if people like those, they should let me know, or if they don't like them. I mean, I thought more information would be good for you guys, but if you don't like them, let me know as well, because I won't do it if it's not something that's helpful to people. Okay. All right, so today I wanted to finish up sort of some unfinished business that we didn't get to last week, which was curvature. I wanted to just do one computation, and then we're going to move on to the next chapter. But I want to give people an idea of what curvature is. And so recall that we defined curvature. We talked about arc length reparametrization, and we defined curvature of a vector valued function, or a curve really. Let's say curve C, which is arc length parametrized by function, vector valued function R of S, to be just the magnitude, well, we can write R prime. It's the magnitude of, so it's T prime, but it's really R double prime. So T is R prime if it's arc length parametrized. So in this case is this. I think we defined it last time to be, take the unit tangent vector and take its derivative, do that. But again, since it's arc length parametrized, the unit tangent vector is the velocity vector. Okay, so we can just do that. So it's sort of the magnitude of the acceleration vector when we're going at unit speed. So what does this look like? So let's say we have a path in space, something like this. Well, you can take near any point, what you can do is you can take this oscillating circle, and it's sort of the best fit circle. So let's say our point of interest was right here. Sort of the best fitting circle that you can put on that curve. And then you can ask about sort of the radius of that circle and curvature at that point, which is denoted kappa. I should have said that before. This is denoted kappa. This guy is equal to 1 over the radius of that circle. So in particular, if you have a very flat region, like over here, over here, I don't know, maybe here or something, you can imagine you're going to need a very big circle to kind of get that curvature. I mean, even that may not do, but and so the radius is going to get very large, which means the curvature is going to get very small. 1 over a large number is very small. On the other hand, if you go to like a different spot where you're really turning, like way up in here, you need a very small circle to kind of get the perfect fit. Too small for me to move it around. The circle is going to vanish. Okay, something like that, right? So here you have a very small radius, and of course then your curvature becomes very large. 1 over some very small number is very large. So how do we see this? So let's just look at a simple problem. I mean, we define this thing here using this formula, but now I'm telling you it's really something like this. That's what the geometric meaning of it is. And so let's just verify this formula for a circle. Of radius r. Of course, the best fit circle for a circle of radius r is a circle of radius r. All right, so what's the solution? Well, what you need here, which is the very hard part of if you were to try not to use some of the other formulas in the book, but rather the definition I've given, is to get the arc length parametrization. However, for a circle, just like for helices, this actually isn't so difficult. And so you can check that R of S is, which, I mean, and this is of course not the only one, depends on where you start and end, but if you just take cosine of S over R and R sine S over R for S, well, of course, S has to be between 0 and the length or perimeter of a radius R circle, which is 2 pi R. This is a unit parametrization. Sorry, arc length, my bad. Sorry. Arc length parametrization. So, and indeed, let's just check. I mean, we're going to need this. If we're going to calculate curvature, we need to take the second derivative. So along the way, we'll have to take the first derivative. So let's take a look at the first derivative. We take R prime of S, of course. We just take the derivatives of each of the components. Remember, R is a constant. It's the radius of our circle. But we do need to use a chain rule here. So we'll get R times sine of S over R times 1 over R, which just gives us sine of S over R. Negative sign. And then here we just get a cosine of S over R. Now, you can check quite easily, right? If I take the magnitude of this for any S, I get 1, right? I get cosine squared plus sine squared. So that's going to give me 1, I mean square root. So this is indeed an arc length parametrization. And so now however, we're interested in curvature. So we want to take the second derivative or the acceleration. And here we'll get minus cosine. Well, I need my chain rule. So I need 1 over R times cosine S over R. Whereas here I have 1 over R, again, a minus sine S over R. And this is a vector, and I did notice this also on the exam. And I was really unhappy. This one I was unhappy about. So I did notice that on a significant number of problems, people put vectors in for dot products. So a dot product is not a vector, it's a number. And just like a magnitude is not a vector, it's a number. So they're very, very different like entities. Like one is a banana and the other one is like a planet. I don't know, right? Like they can talk to each other, I guess. Bananas grow on planets. So I don't know, like they're different things. So make sure to be very careful about your inputs and outputs, what you're writing down on exams and what kind of answer you're giving. Okay. That upset me. Sorry, guys. Okay, so now if we want to take the magnitude of this, of course, we just take square root of the squares of the components. So I have a 1 over r squared, cosine squared, s over r, plus 1 over r squared, sine squared, s over r. And then you can pull out the 1 over r squared, but of course you have a square root, so you get 1 over r times cosine squared, but sine squared is 1. So indeed, you do get the verification. This is what we expected, of course. This is not, I mean, we're just verifying something. We expected this to be 1 over the radius. So curvature does give you a real good sense as to how fast the direction is changing of some curvature, which can be, of course, of very good use if you're considering some models. All right. But that is all I want to say about vector value functions as they're defined in this book for now. We'll maybe come back to them towards the end of the course. But right now, we're going to really move away from this, and we're going to get started on chapter 4. And most of what we do in chapter 4 is concerned with scalar functions, which means it's going to have some inputs and it's going to output a number. Okay. So, but this is really the beginning, I would say, of multivariable calculus. This is the proper place where we're going to start thinking, okay, now we're doing multivariable calculus, or at least starting to. Because indeed, we're going to consider functions f, which take in a domain, which I'll write as say D, and this domain will generally be in some space that's going to be higher dimensional than 1, so Rn, and can, in this class, we mostly think about n equaling 2 or 3. But you can, of course, apply these methods to higher dimensions. And we'll return back a function R. We call these functions of several variables, or scalar functions of several variables. Scalar meaning where it goes, what kind of thing it returns. So some notation in this case. So D, of course, is the domain. D is your domain of F. Oftentimes, F will not be defined everywhere in your space, but on some nice subset that you can describe. This guy, what's this guy called, if you're talking about functions? What? Huh? That's all real numbers, correct. Okay, very good, thank you. I appreciate the volume. I can't hear. Okay, but in reference to a function, your function will take a domain, and if I write this other side, what is this other side called with respect to F? People know? You can be shy. You can say, I don't know. This is like the first time this has happened. This is great. I'm really proud of all of you. No, really, like, because mostly people will say range, and that's not correct, right? Because range is actually the set of values that are actually hit over here. So you can have a larger subset on the other side that you're going to, and still, you call that the codomain, actually. The range is something slightly different. So this guy is all real numbers, as was pointed out, but in context of the function, you would say it's the codomain. That's the grown-up thing to say. And then the range is the set of values that are actually hit by the function. You may ask why we separate those notions. I'll tell you about it during office hours. Okay, so D is the domains. There's other notation. Of course, if we want to kind of manipulate these functions, oftentimes it's good to list out the variables that we're using, the independent parameters. And so here we'll have n equaling 2. This will be the dimension. Take in 2 inputs, 2 variables, and return a number. N equaling 3. Write f of x, y, z. This is a very common notation that we use. And then if we just have n equaling n, general, I usually stop with we're sort of at the end of the alphabet. So we'll just number the variables x1, x2, up to x of n. It's kind of a common thing to do. So this is just notation for manipulating functions, or for writing down functions and dealing with them. So let's maybe start with a problem where we're asked to find the domain and the range of a multivariable function. So this is actually, as we'll see much later in the course, understanding the domain of a function has big implications in multivariable calculus. Very big implications. So certain things depend on the sort of the structure of the space of the domain. One variable calculus, your domains are usually going to be like intervals, right? What can you do with like an open set in one dimension? If it's connected, it's just an interval. It's not very interesting. In higher dimensions, there are a lot of open subsets, even in the plane, right? You can take a little, you can take whatever you want, like a little blob here. You can cut out a hole in the blob. You can do all kinds of stuff. And so all of a sudden the functions becomes very sensitive to the space that they're defined on. Okay. All right, so let's do a problem. Let's get our brains working here. All right, so what is the domain and range of the following function? I'll take 3 variables, f of x, y, z, and we'll take the square root of 9 minus natural log of x squared plus y squared plus z squared. Looks fun. Okay, well, what do people think? Can people rule anything out right away? You see some things that might not be in the domain? Negatives. Okay, thank you for that answer. And the idea being, right, so I think what you mean, when you said negatives, is you can't have this thing be negative, right? Because what I'm searching for with the domain is actually some 3-dimensional blob, right? So if I hear negatives, I'm like, I've got 3 dimensions. What do I mean negatives? But I know what you mean, and you're right. We do have to kind of consider when this is negative. That's true. But if I look where the x, y, and z are, where the coordinates for my points in the blob are, they're going to come in here first. And I know that natural log is defined where? It's defined when, if I take ln of a, what does a have to be? A has to be a positive number. Luckily, this is non-negative, but there's one point for which it's 0. What is that point? The origin, right, 0. So I can certainly say right away, this is not in the domain, because it doesn't make sense to put that in to natural log. It's not going to give me. But now let me take the gentleman's point about taking the square root of a negative. The other thing we need to check is that this quantity here is positive, or non-negative, I should say. So also, 9 minus natural log of x squared plus y squared plus z squared must be greater than or equal to 0. And let's do a little manipulating. So this, of course, I can natural log, well, it is what it is. I can take it to the other side. Exponentiation is an increasing function, right? I take the derivative of e to the x, I get e to the x. That's always non-negative. So it's an increasing function. And what that means is I can apply it to an inequality and it won't change the sign, right? So I can exponentiate both sides of this inequality and I'll get e to the 9 is greater than or equal to e to the natural log, which is just whatever that log is, log of whatever is being put into the log, I should say. So I get this. What is that describing? So I've e to the 9 is some number. What is this inequality describing? Huh? Sphere. Oh, thank you. I love it. I feel like people are speaking my language here. Okay, it is a closed ball. The sphere is the boundary. If I look at the equality, then I get the sphere. But the whole thing is a ball. So this is a ball of radius, closed ball, meaning it includes its boundary, of radius e to the 9 halves. So, and anything satisfying this inequality will indeed be in the domain, except, of course, the origin. So, we could describe the domain as just using inequalities. So I'll just write it out. The domain consists of all points x, y, z, such that we have this inequality, 0 is less than x squared plus y squared plus z squared is greater than or equal to, or sorry, is less than or equal to e to the 9 halves. So if you were taking an exam and you had a problem like this, I think just writing this is probably okay. Again, I like seeing the language because it makes me understand that you understand what's going on. But that's what we're looking for, this inequality. So what about the range? Well, when we achieve equality here, when this is an equality, we're going to get that this is an equality. So we'll have that this whole thing is the square root of 0. So 0 is in the range. Of course, the range of square root function doesn't have any negative numbers. And if this is getting big, we're going to start tracing out all of the numbers above 0. So the question is, can this whole thing get sort of arbitrarily large? What do people think? How many vote it can get arbitrarily large? How many vote it cannot get arbitrarily large? Okay, I'm with the first group. I think it can get arbitrarily large. And the reason is because you remember that what does natural log look like? Guys, what does it look like? It's, you take e to the x and you just flip it over the x equals y line. So it looks something like this, right? That's probably growing a little too fast, but okay. Looks like this. Now, this quantity can get very big, right? Or sorry, it can't get very big. It can get very small. This quantity can get very small, right? Because it's constrained. All we have is that it's in this ball. So this quantity can get close to 0. So that means that we can get very close to here, and then the natural log is going to get very, very negative. And when we take a negative of a very, very negative number, we get a very, very positive number, very large. And so this whole quantity can get quite big, or as big as we want it to get. And so indeed, we get everything from 0 to infinity. Okay. Okay. So the feature, this example is kind of an approachable example, because if we just replace x squared plus y squared plus z squared with t or something, that's a one variable problem. So really the only translation is just kind of doing that. When you have more complicated functions, it can get more complicated. And so, well, I'll let you work through some of these things on the homework. So one of the ways that and one of the reasons that we study the two-dimensional case quite a bit is that we can visualize in graphs of two-dimensional functions. There's something we can do for three-dimensional functions as well, but it's a little bit, well, it's a little bit more difficult. So again, I think I've already mentioned this in previous lectures, but let me just say it again. So if I have a function f in one variable calc, you all know how to write the graph of it or draw the graph of it, at least in principle, right? You just take all pairs of points in the plane that satisfy the equality or the equation y equals f of x. These are pairs of, there's a Cartesian coordinates x, y satisfies this equality. So we want to be able to do the same thing. And as I mentioned before, this is a function of one variable, but what you need to do to draw the graph is you need the number of dimensions to equal the sum of the dimensions of the domain and the codomain. So 1 plus 1 is 2. That's why we have a two-dimensional picture here. Now, if we're going to go up dimensions and we want scalar valued functions, there's only one place where we can really draw pictures like that. And that's when we're taking two variables as our input. And then we're going to get a three-dimensional picture. So we're going to draw our axes. And now the idea is we're going to look for all solutions to the equation z equals f of x, y. So you can imagine, I think you can imagine, I can't seem to draw it, but we'll try to one more time. There we go. Oh, I always do this wrong. So you can imagine a function on the plane, or well, defined on the plane, say. Nope. And you're just looking at, I'm just going to sketch it here. Looking at all values that that you'll get. So you'll get, if you have a point on this graph, it's just a point in three-dimensional space satisfying this equality. That's it. Of course, because it's a function, you know that as long as you're on the domain, there will exist exactly one point lying above it, and namely, this will be given by x, y, f of x, y. So if you know what x and y are, you can easily find the point lying above it by just evaluating the function. Of course, if you go to three variables, things get more difficult to understand, right? Because now you need 4 dimensions. So, well, you can indeed do sort of movies, but to understand that, well, I want to kind of talk a little bit about contour graphs and level curves, or full graph. So to understand this, we want a notion of a level curve or level set. There's also, they call them for functions of 3 variables, you call it level surface. This is 2, n equaling 2. This is n equaling 3. And in higher dimensions, you call it level sets. All right, so what are these? Okay, well, let's take a look at an example. And again, I'm going to do, everything will be by analogy with 2 dimensions, n equaling 2, but hopefully we'll have time to talk a little bit about how you can use this to see level surfaces and maybe get sort of pictures of what 3-dimensional functions look like. So let's say you look at the function as the following function. So consider f of xy equaling x squared plus y squared. Right. So this function is not hard. This is just a paraboloid. It's concave up. And if we want to draw the graph, that's also not hard. So because this is the graph of this is just a quadric, which is something we've worked with before. So the graph is given by the equation z equals x squared plus y squared. And you can, I'll just briefly sketch. You know, you have this kind of bowl like this. Now, what you want to do for a level set is you want to take your z trace. Okay, so the level curve in this case is dimension 2 variables are the inputs, so level curve at say 0, and we'll look at a couple of other examples, is just taking z equal to 0 equals x squared plus y squared, which doesn't look much like a curve, it looks like a point. So this is just equal to the point 0, 0, just the origin. However, if we go to the level curve at 1, we'll get 1 equals x squared plus y squared, and we do indeed see here, we get the unit circle. And we can do a level curve at 2. Of course, here we get a circle of radius square root of 2, and so on and so forth. Now, what you do, so this is something you can do with functions of 2 variables, functions of 3 variables. Once you get to higher dimensions, it's harder to picture it, but you can still talk about level sets. And the idea is you can try to understand the function by just sort of looking at a movie of your level sets. And the way we understand this for functions of 2 variables is to see the contour graph, contour map. So what you'll do here is you sort of take each of these level curves, you space them out as I did up above equally. So it doesn't have to be in increments of 1. It could be in whatever, even increment you want. I mean, you go 1/2, 1/4, 1/3, whatever you want. And then for each of the level curves, you'll draw them. So the first one here, you draw a point, then you have a unit circle. Let's see if I can, so you get some unit circle. And then, you get some, I don't know, I have colors already. Horrible. Get some unit circle, or some circle of radius too. Oops. That's how bad my circles are. So it's not, so the point is that because you're doing this time, this sort of even timing, the spacing will actually tell you something about how rapidly things are increasing or decreasing. So these are, so you can see from this picture there's a bit more distance between 0 and 1 than there is between 1 and 2. And that's saying that these are, you're going a lot faster from 1 to 2. So to connect this up, this contour map up with the actual graph, I did this other little drawing for the parabolic hyperboloid. You can find it. So this guy is, so here's this is a graph up to some translation of a function that looks like z equals, I guess I want to say, sorry, this should look like z equals x squared minus y squared. Something like that. Plus some constant, you know, you probably have to change, you know, x minus something, I don't know. So it's centered somewhere else, but you know, up to some translation, it's something like this. So now if you want to take, so the way to try to go from the graph to a contour map is, I like to think of it as saying, okay, I've got this thing in space, and what I'm gonna do is I'm gonna take like a cheese grater, right? It's some like cheese grater that's equally spaced, and I'm gonna overlay that into my graph. And each of these planes of my cheese grater is going to slice my graph and give me a different sort of color of a curve. So when I did do that, I get something like this. And so when you slice, you get, you know, you'll get this orange guy is going to be the top slice. Then as we kind of move down to z, I mean, I guess if you wanted to, you could start at z equals 0, but okay, I'll move down and I'll get this slice and I'll get these two lines. And I'll move down a little more. And when I look at this slice, I get these blue, this hyperbola here in the blue. So I get, these are the level curves. Okay, this is what it means, level curve, is you're taking this plane and you're seeing what the curve is of the graph on that plane. To get from those level curves to the contour graph, you just project everything down to the XY plane, but you keep the colors. Sometimes, usually they're colored nowadays when you put them on, when you look on most contour graphs now. But you can just project and you'll get this picture here, which sort of tells you, oftentimes people will label these, you know, so you get like a z equaling 0, z equaling 1, z equaling 2. Sometimes they won't put z, they'll just put the number. So this is the connection between the graphs of functions and these contour maps. Now you can do this with three-dimensional functions too. But now what you've got is you've got a graph in 4 dimensions of a 3-dimensional guy. It's called a manifold, but you've got some 3-dimensional thing in 4 dimensions. Then you take a 3-dimensional flat subspace and you intersect it with this 4-dimensional guy. When you do that, you drop the dimension by 1 and you'll get a surface. That's your level surface at that particular value in time. Let's say time is your 4th variable. When you overlap all those surfaces into one 3-dimensional space, the one we can get our heads in, we see a surface moving in time. Right? Time equaling 0, the surface is here. Time equaling 1, the surface is here, so on. And that's showing us some kind of smooth movie of what the graph of our 3-dimensional function looks like. So I didn't make that movie this morning, sorry guys. So an example of that movie, but you can, you know, maybe one good example, which I think I may have talked about, I don't remember, is you can do something like, you know, time equals, say, x squared plus y squared minus z squared. And for this, you know, if you start with like negative time, well, okay, yeah, let's indulge ourselves. So at t equaling -1, what do you get? You'll get the following equation. You'll get z squared minus 1 equals x squared plus y squared. That describes a quadric that we all know. Does anyone know what this quadric is? This is a hyperboloid, but it's a 2-sheeted hyperboloid. So it looks like this. It's this kind of guy. That's our time one surface. And then what happens is like it's like a stalactite or stalagmite or something. You guys know about that? You guys like gone to spelunking? Got any spelunkers out here? Is there any caves in Kansas? Probably not. It's not much in Kansas. I mean, there's things in Kansas. Sorry. I love it here. It's great. Sorry, guys. Okay, so now at t equaling 0, we get 0 to x squared plus y squared minus c squared. Does anyone know what this is? Got a call hall lately? Get a cone. Get a cone out there. See, there are things in Kansas. Cones. Right? This cone. And then what happens at t equaling 1? Okay, so same kind of, so you get 1 equals x squared plus y squared minus c squared. Or, I mean, I can take z to the other side. We notice now, unlike the first case here, where when z is 0, you get -1 equals this, which doesn't have any solutions. Now when z equals 0, we get 1 equals this, which always has a solution. So we get this hyperboloid, but now it's a one-sheeted hyperboloid. And so what you see there is this movie, right? You see a movie of, a stalactite and stalagmite kind of dripping and dripping and then coming together and then kind of expanding out into a column or something, right? You can see this is the sort of like three-dimensional version of a contour map. Okay, guys. All right. So now, what do we want to do? I want to get a little jump start on tomorrow, and I want to talk about section. This is chapter 4. This is all in section 4.1. Now I want to talk about section just a little bit. We'll talk more about this tomorrow, 4.2. Functions are great. We're interested very much in functions, but we only get so far by drawing pictures, doing animations, understanding domain and range. We're going to want to do some calculus. We're going to want to do some interesting mathematics here with this, and analysis. So 4.2 deals with limits, functions of several variables, like f of x, y, f of x, y, z. We're going to primarily, as in most of this book, we're going to primarily be looking at 2 dimensions. That's our domain. I somehow switched notes. I should probably get back to my other notes. I don't lose them, sorry. So we're going to be interested in limits. I'll upload both of x, f of x, y. And now, we can't do what we did with vector value functions. We sort of had this cheat with vector value functions. The cheat was we can use the one variable definition because all we have to do is take the magnitude of our function minus what we think the limit is. That's a regular old function of one variable with values in R, and we can use the definition of limit there. We can't quite do that here because now our domain is 2 dimensions and there's no way of making it 1 dimension. So what we need here is we need the real definition of limit. And I'm going to give it to you, like it or not. This definition is brought to you by Koshi, who's dead. But great guy. From I don't know, from any account I've ever. So we say So let me give myself a little bit. So let's let F be defined in a neighborhood of, I'll say AB, but not necessarily at AB. So as you know from one variable calculus, limits of functions, they don't really depend on the value of the function at that point. They just depend on its behavior near that point. So when I say a neighborhood, what I mean is that there is some little open disk in the domain of F around AB, centered at AB, for which the function is defined everywhere except potentially at the point A. So this neighborhood notion means there's some open disk around my point for which the function is defined, but it may not be defined right at that point. Okay. The limit of f of x, y, as xy approaches AB, B is L if for every epsilon, I'm just going to write epsilon. That's positive. For every positive number epsilon, there exists delta such that if a point is delta away, namely the square root of x minus a squared plus y minus b squared is less than delta, greater than zero. Greater than zero just says it's not the point itself. If I have any point that's of that at most delta distance away, then f of x, y minus L, absolute value, is less than epsilon. Okay, this is the mathematically rigorous definition of limit. It's a definition engineers should really like. But sadly, you guys are never given this wonderful, because this is a very practical definition. This is a definition that says epsilon's your error. You have some ideal function. You know that whatever the specs are, you can't actually hit that ideal, but you have an error term that you must be within. What is the maximal threshold of the independent variables that will keep you within that error term? That's your delta. Okay. So spend some time and meditate on that as engineers, and you'll be great mathematicians. Sorry? Epsilon. I can't hear you. This here? This is delta. Delta. How's it going?